So it's a pleasure to participate in the Seed Lecture that is given annually to the recipient of the H. Bolton Seed Medal for outstanding contributions to teaching, research, or practice in geotechnical engineering. This year's winner, of course, of the medal is Dr. Geoffrey Robert Martin, and he is, again, well-deserving of this medal award. Dr. Martin is a professor emeritus at the University of Southern California. Dr. Martin has been a leading researcher and practitioner in geotechnical earthquake engineering for over 40 years. Since receiving his PhD from the University of California at Berkeley, where he worked under Professor Seed, he is recognized worldwide for his contributions to geotechnical engineering, earthquake engineering, and continues to make significant contributions to the field to this day. Among his many contributions, Dr. Martin has played a lead role in the development of the geotechnical aspects of the ASCE guide specifications for seismic design of bridges, helping bridge the gap between structural and geotechnical specialists in this area. Dr. Martin's contributions to the geotechnical earthquake engineering span a broad spectrum of the field, including seismic design of earth dams, evaluation of liquefaction potential and the impacts of liquefaction, and seismic designs of bridges and other transportation facilities. Dr. Martin's PhD dissertation on seismic design of earth dams under the direction of Professor Seed laid out the basic principles of the seismic coefficient method of seismic stability analysis. In the 40-plus years since it was introduced in 1966, Dr. Martin's work on the seismic coefficient has been widely used for stability analysis of slopes and embankments, including in the work of M.ASCE and Seed on the seismic stability of embankments, and Bray and Roth on the seismic stability of landfills, and is in fact used by every engineer who employs a seismic coefficient in the slope stability analysis. Dr. Martin continues to make contributions in this area and recently completed work on a significant update of the seismic coefficient method for slope and retaining wall design for the National Cooperative Highway Research Program, the NCHRP. Dr. Martin is perhaps best known for his contributions to seismic design of bridge foundations. He has played a lead role, if not the lead role, in the development of the geotechnical aspects of the ASCE guide specifications for seismic design of bridges over the past 30 years. He has led a lead investigator for the development of the first comprehensive methodology for evaluating the stiffness of both shallow and deep foundations for bridges, and incorporated into a global soil structure interaction analysis of the Federal Highway Administration in 1986. Updates on this initial thesis were provided in 1995. Dr. Martin has been a member of the project team responsible for the geotechnical aspects of NCHRP Project 12-49 for development of the LFRD specifications for seismic design of bridges, and this was completed in 2003. Where his work included development of methodologies for evaluation of the impacts of lateral spreading of bridges and for the incorporating pile pinning effects into the displacement capacity analysis of pile foundations for bridges. Pile pinning effects now widely recognized as a significant contributor to the capacity of bridges on deep foundations and liquefiable soils. He was also a key member of the team that developed the FHWA manual and seismic retrofit of bridge structures published in 2006, and on the recently completed 2008 NCHRP 1270 project on seismic analysis and design of retaining walls, buried structures, slopes, and embankment, in addition to his aforementioned work on slope stability. He was also responsible for the development of the LFR seismic design procedures for retaining walls. Dr. Martin has also made significant contributions to liquefaction analysis as a principal of the Earth Technology Corporation, formerly Fugro USA. Dr. Martin was instrumental in popularizing the use of the cone penetrometer CPT in the United States practice. The CPT now is generally recognized as the preferred tool for assessment of liquefaction potential. He is also recognized for the development of the effective stress site response analysis that incorporated pore pressure generation up to and including liquefaction. Dr. Martin has also made significant contributions to geotechnical earthquake engineering as a practicing engineer. He has done extensive work for Caltrans, the City of Los Angeles, the Los Angeles Metropolitan Transit Authority, the ports of Los Angeles and Long Beach, and the state of California on geotechnical earthquake engineering and seismic safety issues. Dr. Martin's contributions to the profession also include teaching in geotechnical and earthquake engineering. He served as professor of civil engineering at the University of Southern California for over 15 years, including 3 years as chair of the department. Dr. Martin's students now hold significant positions of responsibility in prominent consulting firms and geotechnical specialty construction firms and in the government agencies, including Caltrans. His PhD students have made significant contributions not only to the geotechnical earthquake engineering, but in other geotechnical areas of diversity as bio-improvement of soils. I would like to ask Dr. Martin to join me on the podium. Dr. Martin, in recognition of your contributions to research and practice in geotechnical and earthquake engineering, includes the seismic design of slopes, embankments, and dams, and the evaluation of liquefaction of potential liquefaction impacts, I present the 2012 H. Bolton Seed Medal.
Thank you very much. I really appreciate it. Thank you. Well, first I'd like to thank the Geo-Institute for giving me the opportunity to make this presentation of the H. Bolton Seed Lecture. It has some special honor and meaning to me since, as you've heard, I was a student, a graduate student under Harry Seed. I came to Berkeley in 1962 and spent 5 years working with Harry on the earthquake responsive dams. At the time, in that period, of course, there were the 1964 earthquakes in Nevada and Alaska generating significant liquefaction problems. And at that time, liquefaction was not a design component of any of the design guidelines used for buildings or structures in general. Harry really, I think, took the initiative, and particularly in relation to his thinking on some of the slides in Alaska, that this was an important problem and needed to be addressed. Although my work was on dams at the time and I went back to New Zealand to join the university there for a while, I retained my interest in liquefaction, as I think all the graduate students at the time who were at Berkeley were intrigued by the problems of liquefaction. I think the topic of my lecture reflects that continuing interest in liquefaction. And indeed, the photograph you see on the title slide is actually a photograph of sand boils here after the Loma Prieta earthquake here in Oakland. It's an old stream bed where clearly you can see liquefaction being a problem. Liquefaction has always been a problem in earthquakes for many centuries, going back many years. Every time there's a major earthquake somewhere in the world, there's a liquefaction problem of one sort or another, which needs to be addressed. And certainly if you go back to the Calabrian earthquakes in southern Italy, these were 5 major events at the toe of Italy, as you can see. If I can find the pointer, okay. 5 major earthquakes at the toe of Italy near Sicily. These earthquakes range from magnitude 6 through to 7 and caused major devastation in the area. I think about 50,000 people lost their life. They were intrigued, however, by these strange holes in the ground which were filled with water, and they recorded these on woodcuts. And indeed, they excavated down in the woodcut and found the conventional pipe that we find with liquefaction sand boils. Going fast forward to 2011, 2012, the people of Christchurch in New Zealand also have had 3 major earthquakes in sequence, ranging from magnitude about 6 to 6.3. And each time when these earthquakes occurred, there was massive liquefaction in residential areas. And you can see the sand boils in the streets, the sand enveloping the housing sites, the loss of bearing capacity for a pickup truck. Quite major devastation. In fact, 60,000 houses were damaged to one extent or another by this liquefaction phenomena in the in the Christchurch earthquakes. Every earthquake, of course, has its problems. In Kobe in 1995, major lateral spread problems at the port. Tokyo 2011, known for the tsunami, of course, major liquefaction damage in Tokyo of a variety of forms. Here in Loma Prieta in 1989, bearing capacity problems. Again, more problems at the Port of Los Angeles, Port of Oakland rather, rising from lateral spread. Alaska 1964, the event, one of the events that triggered interest in liquefaction here, major damage to highways from lateral spread problems and major damage to a variety of bridge structures. And Nagata 1964, just prior to the Alaskan earthquake, major liquefaction problems, providing the classic photos now of bearing capacity problems with apartment houses and collapse of bridges. So the problems of liquefaction are well known, and I've chosen to talk a little bit about some of my observations over the years on liquefaction problems, particularly the relationship between pore pressure buildup during the earthquake and volume change characteristics of sands under drain conditions. So there are many damage modes, as you've seen from the slides. The surface manifestation problems, the slope instability problems, lateral spread, bearing capacity problems, liquefaction settlement after the earthquake. All of these problems have to be addressed by geotechnical engineers if they predict liquefaction might be triggered. So the issues in addressing these problems are numerous. One is the buildup of pore water pressure in the first instance leading to liquefaction. There's the post-liquefaction residual strength problem, which governs stability. Post-liquefaction stress-strain behavior is difficult to model following liquefaction. Slope ground displacements are a challenge. Soil structure interaction problems are a challenge. All of these problems are still getting extensive research and improvements in our ability to analyze these issues are continuing. So it's now well over 50 years since the Loma Prieta, or not the Alaskan earthquake. We're still working on these problems. But today I'd like to focus on the problem of pore pressure buildup. So the scope of the presentation then will focus on the mechanics of pore pressure buildup leading to liquefaction. And so I'm going to talk very briefly about historical development of how we handle that. Then I'm going back into the 1970s. So if you'll forgive me, I'm going to reminisce quite a lot about the 1970s, which was a very active period of research at UC Berkeley under Harry Seed's direction. And we're going to talk about this fundamental equation, delta U equals E bar R delta epsilon VD, which we'll discuss. Then I'm going to comment on how the recoverable deformation theory, which plays an important role in pore pressure development, can be analyzed using simple particulate mechanics. A few comments on post-liquefaction volumetric strain, some recent test results on cyclic simple shear tests on dry sands, and finally a few comments on effective stress site response analysis. Well, first of all, comments on historical development. The problem we have during an earthquake is one of cyclic shear stresses. If I can get the, I've lost the pointer. There we go. Where the wave propagation causing site response generates a condition of cyclic simple shear near the ground surface. And this is reproduced in a laboratory context as an equivalent number of cycles of loading. In 1964, when Harry Seed was faced with this problem, I was fortunate that he had a research program where he was looking at the resilient modulus of subgrade soils, and had developed system of triaxial testing for repeated loads. So he could adapt the system with a research student named Ken Lee and start doing cyclic triaxial tests where we had cyclic deviator stresses being applied to the sample. It was soon recognized a few years later that the triaxial simulation was not a correct simulation of the cyclic simple shear mode which the earthquake was inducing, and the researchers both at Berkeley in the 1960s and a companion program going at the University of British Columbia under Professor Finn developed cyclic simple shear equipment you see on the right, which more closely simulated the conditions in the field. These are typical lab test results that they got from such tests, where you see in terms of the cyclic simple shear test, the pore pressures, or rather the cyclic triaxial test, the pore pressures gradually increased. I'm afraid the pointer is not giving me all sorts of trouble. Here we go, okay. As you can see, during the loading sequence, the excess pore pressure builds up progressively to liquefaction. The cyclic component of the pore pressure is due to the cyclic all-round pressures that are generated by the deviator stress. What you will notice is that the cyclic strains that are generated during the simulations are very, very small. And in fact, by and large, they're of the order of 0.1, 0.2, 0.3%, which in a context of something you can understand is if you have a 1-inch high sample and you're subjecting it to simple shear, the displacement's of the order of plus or minus a thousandth of an inch. So the liquefaction pore pressure buildup phenomenon is one of very small strains. In case of the cyclic simple shear equipment, the results are similar. You see the pore water pressure building up very slowly. Again, the strains are very small. What was found in these tests that the cyclic simple shear process generated much faster rates of pore pressure development, such that the liquefaction strengths that were developing from the triaxial test needed factors of the order of 2/3 to be applied to get correct numbers. So the cyclic triaxial test method was gradually, I think, replaced by simple shear type loading equipment. When they started continuing these tests through the early 70s, it was found that there were a number of issues in relation to using the test data for design. The test data was, in terms of the strengths, was plotted in terms of the cyclic stress amplitudes being applied to the sample divided by the normal effective stress versus the number of cycles of loading, getting a so-called liquefaction strength curve. What was found is that the curves were a function of over-consolidation ratio. If the samples which should be normally consolidated were over-consolidated, the strengths increased dramatically. The strengths also increased with relative density. Also, the test data was very sensitive to sample preparation methods, in other words, the fabric of the material. Trying to get field samples, undisturbed field samples, was very difficult with these types of materials, as I'm sure you're all aware. At the time, nuclear power plant siting was becoming a major issue. For example, at the Arizona nuclear power plant siting problem, they had liquefaction problems, and people were trying to carve samples, block samples, to get best undisturbance. The Japanese were using freezing techniques to try and get very good samples. A number of issues about trying to get good material. The influence of K0, the K0 values as they increased liquefaction resistance. How did you determine K0 in the field? There's influence of prior seismic strains. Research was showing that if you subjected samples to partial liquefaction, drained the sample, then redid the test, the liquefaction strength increased. So what was the history of past seismic strain at a site. Influence of sample age was of concern. So, and also two-directional shaking. The shaking in the lab was just one directional. In the field, it's all over the place in three directions. So all these issues made it very difficult to try and establish the conditions for liquefaction in a design problem. And so by the early 1970s, a different approach was being considered by Professor Seed and his colleagues. And that was to go into the field and look at field case histories where, based on the peak accelerations from the earthquake, which induced liquefaction or didn't induce liquefaction, they could calculate what the stress ratio demands were and then plot that against the standard penetration blow count. So in other words, the standard penetration blow count became the critical parameter, the thinking being that the standard penetration blow count reflected all these issues. The higher the penetration blow count, the higher the overconsolidation ratio. So if the samples had been overconsolidated or were overconsolidated, been subjected to previous earthquakes, all this would be reflected automatically in the blow count. Therefore, they could go out into the field and look at all case histories where there had been liquefaction in the past. So this is the liquefaction zone here. This is the zone where there had not been liquefaction, and the boundary between these defined the liquefaction strength as a function of blow count. The types of plots that are used today in these analyses are shown here on the right. Those of us working in the field use these types of plots to establish the liquefaction strengths dependent on the corrected blow counts, the percentage fines. These are the plots we use for magnitude 7.5 earthquakes. For other magnitudes, adjustments are made. Similar plots are available for design based on CPT, tip resistance, or shear wave velocity to establish liquefaction strengths in the field. So once those strengths have been established, then the procedure is something like this, and many of you have been through this procedure. You basically take the SPT data and plot it as a function of depth. You make adjustments for fines content. You then compare the liquefaction strengths with the cyclic shear stress demands from the earthquake. Where the strength is less than demand, you get a factor of safety. If the factor of safety is less than 1, then liquefaction can be triggered in the zone. If it's greater than 1, then it won't be triggered. So this is the basic liquefaction triggering process. If liquefaction is triggered, then one has to evaluate the consequences of that in terms of potential ground settlement, ground deformation, slope instability, etc. So that's the standard procedure, and there are still issues related to how that's being used, but nevertheless, that's where the process is at the present time. So I want to now reminisce a little bit about the 1970s again, because we want to talk a little bit about the nature of the pore pressure buildup process and what are the parameters that are controlling the actual buildup of pore water pressure itself leading to liquefaction. And at the time in the 70s and even today, the process is described as described by Seed and Idris in 1971, which simply says if a saturated sand is subjected to ground vibrations, it tends to compact, decrease in volume. If drainage is unable to occur, the tendency to decrease in volume results in an increase in pore pressure. If the pore pressure builds up to the point at which it equals the effective overburden pressure, the effective stress becomes 0, the sand loses its strength completely and liquefaction occurs. Of course, we now say the sand doesn't lose its strength completely, we talk about residual strength. But nevertheless, the thought is that there's a relationship between the way pore water pressure builds up and volume changes that occur under drain conditions. As a professor at the University of Auckland, New Zealand, we had a great system. We were able to go away on a year's sabbatical leave every 5 years. I decided that in the 1970s to visit again UC Berkeley and also spend some time at University of British Columbia working with both Liam Finn and Harry Seed. The objective was to try and establish that relationship between drained cyclic volume changes and undrained liquefaction test pore pressure increases in cyclic simple shear. So the question first is, how do we characterize volume changes in dry sands? And at the time, in 1971, Professor Seed had a graduate student, Marshall Silver, doing work on doing cyclic simple shear tests on dry sands. And the reason he was doing that was that in the San Fernando earthquake, there was some major settlements of fills. These fills were basically compacted, slightly moist, sandy material. So again, they went to work with the cyclic simple shear test. In this case, it was the NGI wire-bound membrane type of test, and produced results like you see on the screen. You have cyclic shearing stresses being applied, and you're measuring the volumetric strains or change in height of the sample. And again, you're seeing that the shearing strains being applied, simulating earthquake shearing strains, are very low, of the order of 0.3%. So you could do tests on a variety of samples with different relative densities, and you could measure the accumulated volumetric strain after a given number of cycles, in this case 10, plotted against the cyclic shear strain amplitude. So on the left, you see the resulting curve. And the interesting thing about the results was that it was found that the volumetric strains were proportional to the cyclic shear strain amplitude and totally independent of the confining pressure as an experimental observation. The right-hand side, you see the cyclic shear strain amplitude versus the shear modulus. And the interesting thing here is that the shear strain modulus also increases as the volume changes occur. So you have the typical modulus degradation curve as a function of cyclic shear strain, but with number of cycles, it was gradually increasing or stiffening. I think even at this point in time, it was quite clear that the mechanism that was happening here was that the sand particles were in effect slipping and going into denser positions. You have zero lateral strain, so consequently the lateral stresses were increasing as the volume changes occurred, leading to an increase in K0 and hence an increase in shear modulus. So some additional tests were done to establish the database for subsequent research, where again a particular sand called the crystal silica sand with a relative density of 45% was used for these tests. And you can see on the top curve that the volumetric strains indeed are proportional to the shear strain amplitude for a given number of cycles, which is a feature of the model or a feature of the test results. The question is, can you develop a constitutive model which would allow you to establish volume changes under a random sequence of loading as opposed to uniform cycles? And the concept was to assume that the accumulated volume change during previous cycles was a memory function, and that for an increment of volume change under a future cycle of 0.2% shear strain, this particular curve would establish the incremental volume change. And so if you made that assumption that the accumulated volume change was the memory function, then you could establish a series of curves which told you what the change in volumetric strain was for a given cyclic strain amplitude as a function of the accumulated volumetric strain. And a simple relationship, a two-parameter relationship, could be established to give you the incremental volumetric strain under a given strain amplitude for these accumulated volume changes. That could be tested by doing a series of tests with random shear strain amplitudes, and you can see from this plot, these plots, that quite a sequence of random shear strain amplitudes were applied to the samples, and the volumetric strains recorded, and the dots are the measured, and the lines are the computed. And so you can see the basic constitutive model now works extremely well, allowing you to compute volumetric strains under any sequence of strain loading. Let's now look at the mechanics of one-dimensional loading of sands, because the recoverable strain in sands during the pore pressure buildup plays a critical role in establishing the magnitude of that pore pressure buildup. And so what happens when you actually load a sand in one dimension? The first loading, you have a nonlinear curve, and if you unload, you have an elastic rebound curve. So the loading of the sand generates a lot of irrecoverable strain. You unload and you have some recoverable strain. It turns out that you can show, and if you first load a sand in one-dimensional compression, the contact stresses on average at grains, individual grains, are actually at the cone of friction. So when you load a sand, you're actually getting sliding at grain contacts. It's like a limiting equilibrium condition. And you'll find that theoretically the horizontal stress versus the vertical stress is a constant. In other words, we're loading under constant K0 conditions, and K0, for example, might be 0.4. If you unload down the unloading path, the particle contacts move within the cone of friction, and you start getting rotation of the contact stresses, and you actually start getting increases in K0 as you're unloading, until the contact stresses move right on the other side of the friction code, and you get vertical slip down here. So mechanistically, if you look at the process, you can envisage that there are two components of strain. One is elastic. You have elastic contact between individual particles. They can compress during loading. You also have the potential of slip at grain contacts. That slip, if the grains are in a stable position, itself will generate additional lateral stress and recoverable strain. And of course, some of that slip will be irrecoverable as the sand grains move into voids. So, having established that concept, we're in a position to establish that relationship between volume reduction during drain tests and pore pressure increase in undrained tests. The concept is, even if you have a saturated undrained condition, you're still getting this slip at grain contacts similar to what you'd get in the drain test. So it still occurs. So if you look at the volume compatibility equation, you have to have the change in volume of the voids, which is simply delta U times the void ratio, or the porosity divided by the compressibility of water, which is the change in volume of the voids under an increment delta U. And so that equals the change in volume of the structure, which is delta epsilon VD, the incremental change of volume, minus delta U over E bar R, which is the tangent modulus on the rebound curve. And since Kw is so large, the compressibility of water is so high, essentially that equals 0 for saturation of ratio of 1. So therefore you have the very simple relationship that under an increment of shear strain, the pore pressure increment is delta U, and that must equal the rebound modulus E bar R times delta epsilon VD, the volume change that would occur in a drain sample under the same cyclic strain increment. So Harry C. didn't like this complicated diagram on the left. He said, well, let me think about it. And so he went back to the good old consolidation equation and said, well, what we have is a sample starting here, and we're going to get void ratio change from the volumetric strain in a drain test. And since we've got to maintain constant void ratio, we're going to get elastic rebound until we come back to the original void ratio, no volume change. So simply then, that is the incremental pore pressure for that amount of volume change. So it's a much easier way of seeing what was going on. So we coined that as sort of a fundamental relationship which is governing pore pressure increases and their relation to volume change. We also mentioned that the shear stiffness increases with the volume changes, and we attributed that to the increase in K0 during the test. So we could establish then a relationship between the cyclic shear stress versus cyclic shear strain, the nonlinear behavior, again as a function of the volumetric strain. As the volumetric strain increased, then the material in fact stiffened, and you could develop a relationship to describe that. So now you're in a position with these equations to look at the behavior of a simple shear test under stress-controlled conditions. You can simulate the rebound characteristics through a series of experimental curves. The ability to model a cyclic simple shear test under saturated undrained conditions and see what sort of results you get. And here you see plotted on the left, the pore water pressure increases as a function of number of cycles. In fact, for various time histories, it's very time history dependent, but in particular on the left you see the cyclic shear stress amplitude or the cyclic resistance ratio theoretically plotted. Now that's for a relative density of 45%, and some of you would immediately say, well, for 10 cycles that looks a little low. In fact, it is low. It should be more than 0.1. So the reason for that is something which we hadn't addressed at the time, and that was that as the volume changes occur, as I said, the slip is going to occur during the undrained test. You get the K0 value increasing. So if you get K0 increasing, then that means you've got more recoverable strain accumulating as opposed to the recoverable strain for a test without the cyclic shearing. And we'll talk about that shortly. So it was felt that this concept was reasonably robust based on the initial results, and this led us to think about system compliance and its results, its effect on liquefaction tests. And the concern was that the system, which we assumed was at constant volume, could have a degree of compliance. For example, membrane penetration was becoming of concern to those in geotechnical engineering, where it was recognized that as you increase the pore pressure in a sample, the membrane, which is under confinement, would gradually expand. So it was nicely dimpled at the start of the test and nicely smooth at the end of the test. So that was generating an artificial volume change in the sample. So you could measure that artificial volume change in the sample, and you could end up with an expression then based on a compliance ratio where delta U was equal to E bar R delta epsilon V, 1 plus the compliance ratio, where the compliance ratio is the ratio of the modulus against the volume change characteristics of the system. And this had a big effect on the liquefaction strength curves. In fact, the liquefaction strengths almost doubled if the compliance ratio was about 1. That is, the system compliance or volume change due to perhaps membrane expansion was about the same as the rebound modulus. So this led us to look at some of the test results which had been published, particularly by Lee and Fitton in 1969. Ken had done a series of tests on 2.8-inch diameter samples with a variety of grain sizes. And he found that the liquefaction strength increased quite significantly as the grain size increased. So from 0.1 millimeters to 10 millimeters, you had about a 30 or 40% increase. The problem is that as with the mean grain diameter, when the mean grain diameter increases, the compliance ratio also increases. And in fact, for a mean grain diameter of about 1 millimeters, the compliance ratio is about 1, which means the volume change you get in the sample from expanding the membrane is about the same as the volume change you get from elastic rebound. So consequently, one could correct these curves to take into account that, and you'll find that in fact the liquefaction strength is totally independent of mean grain diameter. The other concern was degree of saturation. You all know it's extremely difficult to saturate samples, and of course if you have some lesser degree of saturation than 1, the compressibility of water reduces. And there's a relationship published by Koning in 1963 which gives you the compressibility of water as a function of degree of saturation. So one could then establish what the effect of degree of saturation was on the liquefaction strength. And on the top left-hand corner, you see some curves where they all have the same number of cycles to cause liquefaction. But the bottom curve has a B value or degree of saturation of 0.98, requiring 0.2 stress ratio to cause liquefaction, whereas the saturated sample only requires a stress ratio of 0.06. So clearly degree of saturation is a critical component of liquefaction strength. And in fact, a number of researchers in Japan and the US have researched this because it becomes a mitigation concept. If you can entrain air into the water, then you can reduce the degree of saturation and have an impact on the liquefaction strength. You could measure that, as Yohara has pointed out, that if you measure the P-wave velocity, that's immediately giving you some indication of the compressibility of water and can be related back to liquefaction strength reduction. There are other researchers that are in the US that are looking at using chemicals to induce water, or induce air rather, in the water to take advantage of this effect. Another interesting thing that was going on at Berkeley at the time in the 70s was the thought that with these little simple shear tests, the stress distribution may not be very uniform. You have difficulty in mobilizing the complementary shear stresses on the sides of the sample. And the thought occurred, well, let's do some shake table tests on these sands, where we have a shake table. There we go. Have a shake table, and what we're going to do is put a layer of sand on the shake table about 4 feet long and about 3 inches high. So the height to width ratio is very low. So this should give us a fairly uniform shear stress distribution. And we're going to induce the shear stresses by putting a cap, a steel cap on top, which will generate inertial forces and hence cyclic shear stresses. And so tests were done, and pore pressure versus number of cycles to liquefaction curves were established. But it was recognized when looking at the equipment, there was a problem. They had a ballast layer here, which was steel shot. They had a membrane. These samples were saturated by back pressure saturation, but this membrane came across, and so again, you had the possibility of system compliance. As the pore water pressure built up, the system volume would change. And so consequently, this fundamental equation was applied to provide correction factors to that experimental data. And you can see here that the correction factors could range from 0.1, 0.8 to 0.7, depending on the number of cycles. So these correction factors were then applied to the experimental data, leading to these curves which are widely published by Seed and D'Alba, showing the effect of relative density on liquefaction strengths. Another interesting problem experimentally is the data coming out of the lab, of course, was just one directional. And so the question arose, well, what effect does the two-directional shaking have on liquefaction strengths and indeed volume changes? It turns out that at that time, with this same equipment I've just described, Professor Seed had a student, Bob Pike, who was given the task of looking at the behavior of dry sands under two-dimensional simple shear stress conditions using this equipment. And the bottom line was that he found that, and to do this, he put a sample on a shake table, just like I've described, shaking it in one direction. Then he put the shake table on another shake table so we could shake in two directions simultaneously. And what he found was that the volume changes that he got with two-directional shaking were about twice those of just the one-directional shaking. So consequently, those of you who are familiar with the Tokamatsu and Seed procedure for calculating settlement, there's a factor of 2 you use in those calculations. Here's the rebound characteristic prior to loading. We reload and we do the cyclic simple shear test and measure the vertical strain or the volume change during the test. Once we finish the test, we unload again. And you'll notice that the unloading or rebound curve is significantly different from the original curve. In other words, the wedging action of the sand as the volume changes are occurring is generating the K0 increase, which in turn is generating more recoverable strain. So now you have more recoverable strain than might have been assumed in the original tests which we did. So that was of concern because in terms of a constitutive model, you have to have a procedure for establishing how the recoverable strain increases with volume change. So Bob Pike also, in terms of the test results, and you can't see these very clearly, but obviously you've got the shear stress and the shear strain as a number of cycles, and also noted that the shear modulus increased with the volumetric strain. So armed with all this data, you could then predict what the effect would be on liquefaction behavior with the doubling up of the volume changes, given the fact that you have now the unloading characteristics. You have the shear modulus parameters, you have the volume change parameters, so you can go ahead and apply the delta U equals E bar theory, and then compute the pore pressure increases. So again, you'll find that these are the results of that theoretical analysis, and you'll see these are the pore pressure versus number of cycles curves, one directional shaking, two directional shaking, then the resulting liquefaction strength curve. So you see that with the two directional shaking, you have a reduction in the liquefaction strength of about 20-odd%. So this is yet another factor which had to be applied if you wanted to use lab testing for liquefaction strength evaluation. So you can see it's very difficult to do these lab tests. At the time, since we're talking about cyclic shear strains as being the controlling parameter as opposed to cyclic shear stresses, the concept arose, well, let's continue doing strain-controlled cyclic simple shear tests when we do further research. And at the time, Professor Finn, who was involved in this, had a student called Shoba Bhatia, who utilized the cyclic simple shear equipment which they had at the University of British Columbia. This was an interesting device which had rotating side plates using a mechanism that was established actually by Roscoe at Cambridge. And the concept was, well, let's forget about saturating these samples. Let's just do constant height tests. So what you did with the concept of constant height, well, you have this frame, and you can apply your initial vertical effective stress with the bolt system you see at the top. And then you maintain that sample then at constant height and can start the test. And of course, you're going to get volume change in the sample, which will reduce the vertical stress that you're measuring. And the concept was that reduction in vertical stress would be the same as the increase in pore water pressure had you done a test, a normal saturated test in simple shear. And this was confirmed by a series of tests that this, in fact, technique of constant height sample testing with monitoring of vertical stress was an effective way of doing liquefaction tests. So not only that, they instrumented the sides of the simple shear box so they could actually measure the lateral stresses during these tests. So now you have a method where you can do a bunch of undrained tests by using the constant height feature, and you can do the same tests with the same strain amplitude sequence with both constant height and drain conditions. So you have two tests, same strain amplitudes, and you have a very robust way of checking the basic theory. These test results are not from Bhatia. These are actually test results from, I think, the University of Texas with a student of Rathje's, I think, Hazababa, I think her name was, where you can see the typical test results you get from this type of testing. You get the cyclic shear strain being applied, the pore pressure increasing, then the cyclic shear stress gradually diminishing as the pore pressures increase, and you can see the typical hysteresis loop as the pore pressures are generated. This equipment at the University of Texas is slightly different. It was actually, these tests were done on saturated samples, and saturation was controlled by putting the actual test equipment in a cell. I'm just going to look at the right-hand slide, and here you see a series of tests done both drained and undrained at two different shear strain amplitudes, and the volumetric strains and the drain tests compared with the pore pressure increases in the undrained constant height tests. And you can see there's a unique relationship between volumetric strain and pore pressure increase, confirming the concept that volumetric strain is a key component of pore pressure increases. I guess I really need to look at this left-hand slide, which again is from a paper from Hazababa and Rathje, where they measured pore pressure increases as a function of shear strain, compared data with some tests done by Ricardo Dobry for both 1 cycle and 10 cycles of loading, and establishing a unique relationship again, this time between shear strain and pore pressure increase. Professor Dobry also was doing research on strain control and strain relationships with pore pressure development in the late 70s and 80s, and developed his own strain-dependent relationship with pore pressure increases. The interesting thing about this type of plot, which we must recognize, is that once you get down to strains of the order of 0.01%, essentially you don't get any permanent volume changes in cyclic simple shear, or for that matter, pore pressure increases. So there's a transition strain of about 0.01 to 0.02%, where we don't have to worry about pore pressure increases during testing. Well, Bartier was able to look at a whole variety of conditions comparing undrained behavior with the drained behavior using the volume change relationships we've been describing, and in fact validated both pre-straining effects, and this slide is not a good slide. I'm not going to attempt to describe that, but the right-hand slide shows theory and prediction for a random sequence of stress cycles. Also at the same time, Bartier did a range of tests, again looking at overconsolidation ratio and the effect on liquefaction resistance and the ability of the fundamental model being able to predict the effects of overconsolidation ratio somewhat successfully. Interestingly enough, looking at the left-hand figure, as I said, she could measure lateral stresses. For a normally consolidated sample, starting off with K0 of 0.39, as you can see, during the increase in number of cycles, you're gradually increasing K0. If you start off with an overconsolidation ratio with K0 values around 1 for an overconsolidation ratio of 4, you'll find during the tests the actual K0 values actually reduce down to similar values with a normally consolidated sample. So this interplay between volume change and overconsolidation ratio becomes an important factor. Of course, as the overconsolidation ratio increases, your volume change reduces, and of course your liquefaction strength increases. I want to comment just briefly now on particulate mechanics. I think particulate mechanics, people have researched particulate mechanics looking at the ability to simulate liquefaction problems. It's a very complex problem, but you can take a very simple viewpoint on the problem. So since recoverable strain is an important component of the liquefaction behavior, it's worthwhile trying to see if a very simple particulate mechanics model can tell us something about recoverable strains. And so you can take a sample in 1D compression and start looking at the load and unload behavior. And the first component of the problem is if you have, and if you're simulating this problem by spherical spheres with some elastic property, then you can look at the elastic deformation of just one sand particle against another, assuming they're uniform elastic spheres. And the first component of that problem is it's all recoverable elastic deformation. So you find that in the vertical direction, the recoverable elastic strain, incremental strain, is the same as the vertical strain. In the radial direction, you've got the conventional elasticity equations where you have delta epsilon 3e, 1 minus mu delta epsilon 1e. Then you have the Hertz equation for spares in contact, where the strain is equal to parameter S times sigma 1 to the m. And typically for sand grains, m is about 0.3 to 0.5, and we take Poisson's ratio about 0.2 to 0.3. So that's for elastic spheres in contact. Then you have the slip condition, where we've mentioned at first loading, the contact stresses will be on the cone of friction. And so for limiting equilibrium, you have two components in the 1 and 3 direction equals to tan phi sub u plus beta. And for quartz grains, phi sub u is about 23 to 27 degrees. So if we look at the slip deformation of grain contacts, you can have two systems. One is a stable system on the left, where when the grain slip occurs, the grain is slipping in a stable configuration between other grains, and consequently the lateral elastic deformations accompany the vertical deformations to maintain zero lateral displacement. So you're getting this additional recoverable strain developed along with an increase in K0. In an unstable system on the right, you get particles slipping into a void, and we're not interested in non-recoverable deformations, so we'll forget about that. So the resultant recoverable strain then is equal to the recoverable strain from elastic contacts plus the slip strain, the recoverable slip strain. Interestingly enough, you can do some tests in the laboratory loading and unloading sands in 1D compression. And what you find is that as you start doing this, of course, you get some non-recoverable strain, but the more and more cycles you do, the more and more unstable contacts are eliminated, and you end up finally, maybe after 100 cycles, with a closed loop system unloading and loading elastically. And so, as I said before, if you take a random isotropic assembly of spherical particles, Horn in 1965 generated the rationale for slip at grain contacts at first loading. And in general, then, he came up with the expression that the incremental slip deformation was equal to minus R times delta epsilon 3, where R is a function of the structure of the sand. So if you do a lot of substitution and integration, and we've already talked about too much mathematics, you end up with equations describing the loading and unloading cycles in one dimensions. And these equations generate data that you see here, where you see vertical stress against vertical strain, load and unload. And so loading, you have slip at grain contacts, giving you the K0 value, it's a constant. And then when you unload, you go through a set where the area where the contact stresses are within the cone of friction, but finally you get slip in the reverse direction, and the unload curve in terms of sigma 3 comes along here, and then eventually you get slip and a drop down here. So that can be compared with experimental data after Hendren. Hendren did a bunch of work on looking at 1D compression, and indeed the unloading curves and lateral stress curves agree quite well with this simple theory. So then you can go on and say, well, what happens to the rebound curve if you induce some cyclic simple shear displacements, increasing K0, and indeed you can generate theoretically this increase in elastic rebound, where this is the normal unload curve. You develop the additional volume change from cyclic simple shear to a K0 of 1, then unload, and you can see you've got significant increase in recoverable strain. Here's some experimental curves which by and large agree quite well with the theory. So you have this additional complication in developing the constitutive model of a recoverable strain which is varying as a function of the volumetric strain. So basically the fundamental theory we've talked about, I think, is a robust model. There are complexities with it, but nevertheless in terms of explaining the incremental pore pressure buildup that occurs and its relation to volume changes, I think it's been quite successful. Once we get liquefaction, of course, we get much larger cyclic shear strains, and consequently one can imagine then that the sand structure, once you get this cyclic mobility developed, or ground lurch as we call it sometimes during earthquakes, the sand structure will be totally remolded and take on a different configuration. Whereas when we're building up the pore water pressure at low strains, remember these are the order of 0.1, 0.2, 0.3%, it can be envisaged that the sand particles themselves are essentially positioned in the same structure. So if we look at the curves published by Tokumatsu and Seed, we find in terms of the volume changes that are occurring post-liquefaction, we find that the values prior to liquefaction are of the order of the same elastic rebound strains we get from the test data. Once you get into the liquefaction range from this chart, you find that the volumetric strains become significantly greater, 1%, 15%, etc. And this reflects the fact that the sand structure is now being totally remolded. It becomes a virgin sample, and so when you reload it again, you're outside the original elastic recoverable range, and you're into a brand new sample and getting a lot more permanent irrecoverable deformation. So I'm looking at the wrong curve. Sorry, here's the volumetric strains. These are the cyclic mobility curves. So prior to liquefaction, we're getting 0.1, 0.2, 0.5%. Once we get liquefaction in this range here, the volumetric strains are 2, 3, 4, 5%, which are typically of the values that you'd get for first loading a sand, a virgin sand. Now, we've talked about volume changes, and in these early test sequences, people were testing this crystal silica sand, and they were testing Ottawa sand, were the two main sands being tested. So the question you might ask is, do the volume changes during cyclic simple shear vary from sand to sand? And I guess both test programs at USC and UCLA under Jonathan Stewart in recent years have been looking at volume changes under a variety of different sands. And here you see some data published by Jamal Ramadan, a USC graduate student, where he looked at a wide range of sands. This just shows some of them. There are many more. And you can see the grading is ranging from fairly uniform to well graded. And if you look at the volume changes, and these were tests done at 0.1% strain amplitude, you can see that they vary enormously. Crystal silica sand is somewhere in the middle here. So if you take the test data from crystal silica sand, depending on what type of sand you have, it can vary enormously. And all these sands are prepared by impluviation, so there's no change in method of preparation. So the question is, can you find something that would describe how you might expect the volume changes to vary from sand to sand? Is there one parameter like a D50 or a grading uniformity which would control this? And having looked at, and these are all quartz sands incidentally, you find that the interesting correlation is that the volumetric change for a given relative density is in fact proportional to E minus E min. That is the void ratio minus the minimum void ratio. So for a given relative density, of course, E min will vary and E max will vary from sand to sand. But for a given relative density, of course, the E values will be different. And so, but if you plot E minus E min, at least for volume changes occurring under strains less than, say, 0.5%, there seems to be a good correlation. In other words, the closer the void ratio is to the minimum void ratio, the volume change is less. Likewise, you'll find, again, if you test these samples at different overconsolidation ratios, you'll find the same relationship seems to apply with overconsolidation ratio, and of course, the volume changes are substantially less with overconsolidation ratio. So this raises the question, well, wouldn't you expect a big change in liquefaction resistance from sand to sand at a given relative density, since these volume changes are changing quite a lot? So here are 4 sands, Nevada, silica number 20, which is crystal silica, Monterey, and a Fan F110. And so rebound curves, just straight rebound curves, were established for all these sands. And what you notice is that for these sands that give the greatest volume changes, they have a totally different recoverable strain energy. In other words, it's much more than for the sand here, the recoverable strain energy is much less. So there's a compensating effect here, because whereas the volume changes for Nevada sand are much greater, the rebound characteristics are much less. So that means that there's a compensation in terms of the pore pressure increase. So if you apply the fundamental theory to establish the liquefaction strength curves, you'll find that the differences are not that great, although there are differences. So it would seem to suggest that we don't have to worry too much about the variation in liquefaction resistance with the type of sand. On the other hand, you have to worry about Tokamatsu and seed, and those of you that are working in the field use this plot all the time to assess the volume changes occurring in sands under earthquake loading, in other words, the settlements. And these are a unique set of curves, and just like liquefaction curves, are a function of blow count. And so you could say, well, isn't that the same as for liquefaction curves? The blow count reflects all these things, the K0, the pre-straining, et cetera, but in fact, these blow count curves were established by straight relative density correlations from the original data set that was used to develop these curves. The original data set was the volume changes for crystal silica sand established by Silver and Seed back in the early 70s. So this data, the settlement data, hasn't been correlated with sufficient case histories as for liquefaction correlations on with respect to blow counts. So therefore you could argue that there's some potential errors in these curves depending on the type of sand that's been looking at. So I think there needs to be a study done to reevaluate these settlement characteristics in terms of some of the data that's coming out from the new cyclic simple shear volume change tests. Well, you could argue, well, now we've got a constitutive model for pore pressure increase. Can we put this into a site response analysis to do an effective stress site response analysis? Because we can, we'd like to know how the pore pressures build up as a function of time using a constitutive model such as the one we've described. And this was done in the late 70s by Lee and Finn to develop the program DESRA, and more recently at USC modified the program. But obviously the establishment of the parameters for these tests becomes a challenge in a practical sense, because we're not going to take samples in the lab and do a bunch of tests to establish rebound characteristics and volume change characteristics. So we have to go through some pragmatic approaches to establish the basis for doing one of these analyses. And first of all, we need to establish a nonlinear backbone curve. So what we do is we take the conventional modulus reduction curves as a function of strain and convert that into a nonlinear backbone curve. Originally it was assumed hyperbolic. Now we have a different Masing model. We do suppress the strain hardening. In other words, we don't complicate life by recognizing that the modulus will increase with volume change. We suppress that. We've also got to degrade the backbone curve as a function of pore increase, and we use a degradation parameter approach established by Vasetic at UCLA. Then you've got to get some representative elastic rebound curves. You've seen how difficult it is to establish those rebound curves. So we use a pragmatic approach and establish some curves just based on N1 values as best we can. And then we've got to get some volume change parameters. We need 2 volume change parameters. And again, these parameters are based on rough correlations with blow counts. Then, of course, like all these constitutive models, you have to calibrate them to make sure they're making sense in terms of your liquefaction strength curve you've established from blow count criteria as we've previously described. And so there's got to be some adjustment of these parameters. Usually the volume change or rebound parameters are slightly adjusted so that we can match a field liquefaction strength curve when we do a simple shear test. So also we have to have some potential for pore pressure dissipation or redistribution during the analysis, and you need to note that the coefficient of compressibility, which is in the consolidation equation, is 1 over E bar R, so it's also a nonlinear function. So we've got to make some judgments on how to use that. So it's not simple, and but nevertheless, effective stress analyses, I think, are a wave of the future. There are studies done on elastoplastic type models to do effective stress analyses, such as Misko Kubanowski in New Zealand, Peter Byrne at UBC with the UBC SAND model. However, I think, from my perspective, I think in the calibration process of some of these models, they should look closely at the pore pressure buildup phenomenon. In other words, a constitutive model should be able to function in the drain domain and predict volume changes under drain tests if it's going to be a robust type model for analysis. It also should be able to reflect changes in K0, because I think the pore pressure changes in a K0 situation, if it's over-consolidated, will be somewhat different from a normally consolidated material. So why do we want to do these effective stress analyses? They can become quite important. They're obviously not done on a routine basis right now. They're complex. But here's a simple example which illustrates some of the issues. Here is a multi-layer system. So you can see that there are sand layers of varying blow counts, and factors of safety have been established based on conventional procedures ranging from 0.65, 0.12, 1.2, 1.42, etc. So an effective stress analysis was done and the pore pressure increase is evaluated. So let's just go down and see what happens. The top layer here, you can see that it's got a factor of safety less than 1, but the pore pressure increase has only been 17%. Hey, what's going on? Here we have one that did liquefy at 6.6 seconds, which would be expected. Factor of safety 0.77. And what's happened is that this layer is now acting as a base isolation system and preventing the shear stresses from getting into the upper layer, which is now not liquefying. Likewise, we see here at 14.9 seconds, this layer liquefies, but it's got a factor of safety of 1.2. How come? Well, this layer liquefies at 11.6 seconds, and excess pore pressure on this layer is being redistributed into this layer, causing it to liquefy. So there are important aspects of these types of analyses which can have a particular impact on our understanding of a liquefaction problem. Here's another example illustrating the effects of liquefaction. In this case, it's a multiple layer system. And I think what we all recognize, we don't have nice, simple systems in the field. We have multiple layers. If you do a CPT, you'll find that factors of safety are varying enormously from layer to layer. It's difficult to figure out what's going to go on. This site has, at 50 feet, it has, incidentally with these models, we degrade the pore pressure and we degrade the strength down to get residual strength. But these are the cyclic resistance ratios on the right-hand column. And you see this layer at 50 feet has about a factor of has a cyclic resistance ratio of 0.15. It liquefies first in this analysis, and you can see that in terms of the model we're using, it generates very large lurch strains of about 6%. Admittedly, the model in DESRA does not account for dilation, stress dilation at large strains, but the strain is about 4%. But the interesting thing is that once a layer appears to liquefy, the energy seems to be focused on that particular layer. And although the layers above that layer did gradually build up pore pressure, even though the base isolation system on this layer reduced the stresses getting up there, the large strain potential was focused on that first layer, the liquefied, which I think is another issue, because I think you always want to know where the seat of a lateral spread is going to be. So there's a lot of work to be done on these effective stress analyses, and they're complicated, but nevertheless I think they should be getting a lot more attention than they are right now. So just to summarize then, I think I've tried to illustrate that the two key factors influencing the progressive buildup of pore pressure, the mechanism simply involves the incremental strain-dependent volume change and the associated incremental recoverable volume change to maintain constant volume under undrained conditions. I think that's a very robust model. The complexity is, of course, in the recoverable strain, which in turn is a function of the buildup of pore pressure and the changes in K0 conditions. The observed influence of K0 and previous pre-straining on liquefaction strength of sands can be simulated by the use of this fundamental relationship. And indeed, the one-dimensional recoverable strain behavior of sand can be simulated by a simple particulate mechanics model. So what do we need to do? I think although the pore pressure buildup problem is not getting a lot of attention as opposed to the liquefaction triggering mechanism and with the liquefaction strengths, I think we need to understand a little bit better how that pore pressure does build up, and it's a function of a number of variables. So I think we need to do a little bit more research characterizing these parameters that seem to represent the build-up mechanism. Also, I think we need to do further research to establish the practical use of the constitutive model in non-linear effective stress site response analyses, not only the model I've described, but other models that are starting to be looked at closely. And I think any model that could be used with confidence needs to both simulate undrained behavior and drained behavior. For multi-layer sites with varying liquefaction strengths, effective stress analyses provide key information on the initiation and location of post-liquefaction deformations, and in fact the whole pore pressure build-up process as a whole. And I think what I'd like to do is encourage people that are working with centrifuge systems to look more closely at doing tests on multi-layer sites with different liquefaction characteristics. Right now it seems to me there's a tendency just to use two-layer systems, rather simplified systems, but I think I know it's more difficult to prepare samples, but I think the use of a centrifuge with multi-layer systems with different factors of safety against liquefaction would throw more light on the importance of doing these effective stress types of projects. So I think that concludes my presentation.